Morning, everyone, and thanks very much for joining us this morning. Just a few tips on preventing COVID. Apparently, avoid England at the moment with 50,000 new cases. Always wear a mask when out in public. Wash your hands with soap or an alcohol-based hand sanitizer. Avoid touching your eyes, nose, or mouth with your unwashed hands. And avoid close contact with people who are sick. Cover your cough or sneeze with a flexed elbow or tissue. Then throw the tissue in the bin. Clean and disinfect frequently used surfaces and objects. Our Tech Talks today is on hydraulics in soil and vent, and it's a part of a whole series of looking at what actually happens inside soil and vent pipes and in sewage systems. The philosophy of know-how installed, moving away a little bit from what is in the normal textbooks and looking at how things actually work. Welcome to Tech Talks. Today we're having our presentation at the Geberit Hydraulic Tower. And if you've ever wondered what happens inside a sewage pipe when you flush the toilet or empty the bath or the basin, this is the place to see exactly what happens. The hydraulic tower is located in Limbro Park at Geberit's head office. On the hydraulic tower, we're able to look at various scenarios and to see how the hydraulics inside the drain pipes work. Using two colored waters, red and blue, we're able to see exactly how the air and the water flow and what is the correct and incorrect installation practices. Over the years, Geberit have been looking at the various problems that plumbers face in the installation of drainage, and they've looked at the various scenarios and simulated them to see how we could overcome those problems. And the advantage of the hydraulic tower is that we can better understand what it is that we're doing and how it should actually work. Just about every scenario is covered in the various options on the hydraulic tower. And of course, if there are any new things that come up, is that they are quite easy to simulate and to see what happens in that particular circumstance. Today, we'll just be looking at two areas. We're not going to look at the whole hydraulic tower. That would take us hours to do. And over the next few Tech Talks is that we'll be concentrating on the hydraulics inside drainage systems and trying to better understand what we should and shouldn't be doing. It's quite interesting to, once you start looking at the hydraulic tower and what really happens in it, and you get an understanding of exactly what we should and shouldn't be doing and what we are constantly doing wrong and why we pick up the problems with these installations. So going back to the basics of drainage, which we covered last time, is that the most important thing in a drainage system is obviously air. If you don't have sufficient air in the system, is that you're going to cause siphonage and you will also create the blockages. If you have a look at our ideal fill ratios, is that the pipe size should be sized accordingly to have either a 50 to 80% water ratio to air. So moving on from that, and we'll come back to this a little bit later. When we look at the velocities and what happens in a stack, is that as the water is falling, is the column of air in the middle of the pipe is pushing the water to the sides. And whereas in a stream or in a river, if you think of water flowing down in a river, is that the fastest moving water is in the middle of the river and the sides is quite slow. Whereas here we have this air column that pushes the water to the edge. And that's quite interesting to see in later sections of the Tech Talk, is to see how this actually affects what we are doing. One of the biggest challenges we have in installations, and it's an old problem, that we've always just installed toilets with a horizontal pipe going into the stack. So in other words, we come out of the back of the wall and we turn directly towards the stack. And with the introduction of water-saving devices and the various different pan designs, it's important to actually have a down pipe where the pipe either needs to go down vertically or it needs to go down at a 45-degree angle, and to go down at least one pipe diameter. And what that does is that it creates a little bit of a siphon at the back of the pan when it starts. It increases the velocity as the water is going down into the bottom of the bend over here. and it then flattens out to allow the air to come back into the pipe. And it's an important thing that we should all be doing. Very often we will just take the pipe from this point here and we'll go directly into the side of the pipe, and it works. But when you start getting into multiple stories and multiple opposing connections and that, you then start picking up problems. So in this scenario, we have a whole lot of, on this section of the tower, we have a whole lot of different scenarios. We are going to concentrate on this one at the top here. And as we go through the various hydraulic tech talks, is that we will look at areas. But at the moment, it's just these two here. The important parts of installing a WC is to make sure that when you come out of the back of the wall, is that you have a downpipe, that the pipe drops down and not horizontally. So either at 45 degrees or to drop down vertically. If you look at this scenario, you'll see the two different connections, and you'll be able to see the effects of the flush. And that is why a lot of your pans that are not very well designed don't flush on the first, or don't clear on the first flush. So from this, what we're able to see is what happens over here. This is obviously the incorrect installation, and how we typically do the installations is that we get a big backup of water in this area here. And as it comes through, this area here gets clogged, and we're blocking off the air from going up vertically. On this side, you can see how the water accelerates and then disperses down, and then there's less of a blockage in this area or clog of the water. This can be seen a little bit clearer in this picture, even though the quality of the picture is not great. Is when you try and snip things out of videos, the quality is not always amazing. But you can see here exactly how it is starting to block up, and that stops any air coming up from the bottom upwards. And in this particular instance, it'll work fine. But when you get simultaneous flushes from stacks above or below, you start to create a little bit of a siphonage problem. So the next challenge we face with the hydraulics is obviously with water-saving devices is the fill-in ratio. And we find is that the standards and the SAN says that we must have a 110 or 100 millimeter soil pipe. And what we actually need is that in areas we need to start off with a 90 millimeter. If you look at the size of a trap, is we connect it to a 100 mil pipe, but the actual diameter inside the back of a pan is normally between 80 to 90 millimeters. So going to that one size up is not a problem unless you are trying to flush on less and less water. So in this scenario here, you can see if there's insufficient fill in the pipe, is that the solids get stuck there. So tell us about the terms that you use for
it takes about 2 days to make. So we make out of silicone and netting special rubber O-rings. And we call this a norm term because it's normal. Everyone says, no, ours are bigger, theirs are smaller, we call it a norm term so that we can do a general test.
In this scenario, we've got two identical installations using a 110 pipe with a water-saving system. And the second scenario on the right-hand side has got a 90 millimeter pipe and also the same water-saving system. What we're going to do is take Rana's norm terms, and we're going to flush them down the pipe, and we're going to see the effect of the pipe filling and where the solids stop in the line. Okay. And the winner is Supertube. So you can see from the 110 mil pipe with the red water is that the solids got stuck, and they got stuck quite far back in the line. And so every time we flush is that we then pick up a little bit more solid, and hopefully the velocity of the water that's from the flush will pick up the turd in front and move that on. And the next one will come along and clear that as well. So it's really important to make sure that we understand the hydraulics in a drainage system, especially in big buildings or where we are limited with space. And we start to reduce falls in basements and things like that, where we're limited by headspace, and we try and run it at about a 1 in 80 or 1 in 100, is that really becomes a real challenge. So in order to get the correct hydraulics in a system, it is virtually impossible to do a design using 2 or 3 pipe sizes. If you've got a 50, 110, or 50, 75, 110, to get the correct hydraulics to be able to calculate the under and overpressure in every portion of the job or in every portion of the system is really important, and you can't do that with just a few sizes. And so when we look at the hydraulics and what is happening, is that we have a whole lot of things that we've learned from the hydraulic tower, is that we can see what happens with all of the air, what happens with water, how we can manipulate that and use it to be able to get a better performance in the hydraulics. And over the next while is that we've got a couple of 100 scenarios that we can run through. But what we'll be concentrating in is the ones that are really problematic for us. In the design of buildings is that it's important to really take the plumbing into account and make sure is that you've got the most efficient system. By just using the old conventional design methods, is that we can add an extra meter or 2 into the height of a building. And when we look at a building which is 20 or 30 stories high, that means that you're adding that extra meter or 2 of everything. That's your glazing, it's your facades, your finishes, everything that goes into it. So design of the drainage is very important, making sure that we keep our runs as short as possible, that we make sure that we have the right venting in everything that we do. The venting is probably the most important thing in the drainage system, is that once you have sufficient water and solids backed up in a pipe, it will normally push itself through. If you don't have the correct air, then you start siphoning everywhere, and that is the bigger problem. We all know that payday's on Friday, and when it all stacks up, is that it does go downhill. And the drain itself is, the solids and the water in it will normally carry on moving. You can even drain buildings where you've got a slight negative fall, and provided is that you've got sufficient liquids behind it, it will drain. The new designs are coming up now where we're able to run a pipe horizontally for up to 6 meters without any fall. So we can take the water down from various floors, and using the lessons that we've learned in the hydraulics, and be able to design it so that we can have sections of horizontal pipes. So if you could imagine in an apartment block, every time you go from a duct across to where the main stacks are, that horizontal pipe would normally have a fall of 1 in 60 or thereabouts. And that means is that you're going to have, for every meter of horizontal, your pipe is going to have to drop 17 millimeters or 16.6 millimeters. And that then obviously takes ceiling void and height. So if we're able to reduce that and keep that at level, we could actually have a ceiling void of maybe 150 or 200 millimeters. But to enable us to do that is that the hydraulics and understanding the air and liquid flow is so important. And there's a couple of little clips that we're just going to, or another clip that I'm going to show you in a few minutes, just to see how important the hydraulics in a drainage system are. And from this development is that they're able to drain a 100-story building, and that is the equivalent to 140 toilets flushing simultaneously in a single 110 diameter pipe without supplementary vents. And as we're going through all of the various hydraulic scenarios, you'll see how this all comes into play. And if we don't understand how the air moves and how the water moves, is that we will pick up problems within our drainage systems. So this is a new product called Supertube, and we'll be looking at this in depth in the next presentation. As you can see from what we've learned and what happens with the air and the water, once you can take that and manipulate how it works, is you can create all sorts of benefits. The turbulence in the water is allowing the column of air to come up through the center of the pipe, through that spiral. And by being able to change that spiral from left to right in different places, you can actually drain a lot more water from the system. And that takes us back to our challenges that we have with the solids getting stuck. It's important to make sure that our pipe sizing is the correct size, that we have at least a 50% fill-in ratio. If we don't have that 50% fill-in ratio, is that the solids will get stuck. If we have the velocity behind the water, we'll obviously clear all of that away. But if we don't have sufficient air, is that will then create the additional problems that we are seeing in buildings. So the hydraulic tower is available for anybody to go and have a look at. You'd obviously just have to make an appointment. We will be covering it, every section of it, and there's so many different scenarios. And we'll look at everything that we're going to start off with all the things that we are doing incorrectly on buildings, and we'll address each one of those. And I'd look forward to any comments from anybody to ask what problem that they're having and what the solutions are. We'll be looking at the hydraulics in traps and the design of traps. And typically we all look at a trap and we say, well, it's a U-bend. And through all of the computer simulation and through all of the design philosophies and understanding, is that the shape of the trap has really changed a lot. And new traps now are designed so that they would scour better. In other words, they would clear themselves, they're self-cleaning, and still give us the right drainage rate. And then, of course, to maintain that seal. And when you look at some of the traps and you think, oh, gee, this doesn't look right. It looks like it's going to block and it's going to give us problems. It's amazing to see when you're looking at it on this hydraulic tower as to why they've made those changes and what has come out of it. We'll be looking at scenarios where we'll see how the unders and overpressures are affecting the traps and how they suck the traps out. We'll be looking at overpressure where we will get a movement in the base or in the lower floor pans. When you look at the trap and you'll see the water level is fluctuating up and down as the other toilets are being flushed. And as you introduce second and third flushes, it's simultaneous flushes, is how that water actually pops right out of the system or out of the pan and starts to go up into the back of the system. We'll see how when we release the plug from a bath, what that effect is. And more in buildings now is that we are creating a combined drainage installation that is cast into the concrete. And again, from the hydraulics, it's important to make sure that all of that pipe sizing is correct so that you're getting the correct drainage, that they don't block, and that we're able to design efficient systems that work. The other really interesting aspect of looking at this hydraulic tower and all of the experiments that we've been looking at is to see where we really don't want to put access eyes. Is on the back of the bends and on the back of the junctions, you start to see how the water behaves, and if it has got sufficient solids or toilet paper or hair, is that in those areas where they're typically on the back of a pan, is you don't want an IE on the back of the pan, because it'll push that hair and the toilet paper and that into those little recesses on the cleaning eye. You actually want that to be a nice smooth surface so that it'll constantly wash and scour that fitting. The hydraulic tower is really an amazing thing, and I would urge anybody that has got a major project to make an appointment with Geberit, get them to run through the scenarios, look at the design as to how you're going to put it in, and get the most efficient design for your project. So obviously the tech talks that we do through Umpakati development and training, and Umpakati development and training are there to uplift the standards in the industry. All our training is free. So if our training is based on hydraulics and on the Geberit know-how installed. And so if you have any big projects and you need any training for the installations on the drainage and the water side, give us a call. We'll send out one of our guys, or we'll come out with the truck and we'll demonstrate how to do the work correctly. We're finding lots of failures because guys don't understand the basics of this new technology and how it's installed. Well, it's not new technology, it's old technology, but in South Africa it's relatively new. So please take advantage of the training. It is free. We've got an amazing sponsor through Geberit where we're able to do this, and we want to make a difference to the industry. Thank you. Thanks, everyone.